And here's where we found t and little t. Which then we graphed these on our log graphs, and we were able to find the amplitude ratio and the FU. And we also were able to find K. And this is the same thing, except where we graphed our model with our actual results and come out to very close to what we saw in real life. Here's where we graphed those results. The calculated range and the model data was very close to the same for both. The results for tau and T naught, again, fairly close. These ones were a little different. The 75%, it was just 0.1 off, but the 75% there in the tau came off fairly close, but it was a little off. Here's the results for the FU. In all three cases, 75, 80%, and 85%, they were pretty close. The ARU, again, 75, 80%, 85%, very close to all the same. And here's where we just graphed all the results. The average calculated system parameters, ARU, K, FU, tau, and T naught, and the model system parameters. Here's a plot of a root locus at 85%. Root locus helps us determine the decay ratio that we want. At 45 degrees, you find where it crosses your axis there, you get the 1/500th decay at 45 degrees, 1/10th degree decay at 70 degrees, and quarter decay at 78 degrees. And your critical damping is at 0, and KC ultimate at 90 degrees. And here's the results that we found from that graph. 75% input, the KCD, critical damping, was 0.59, 80% was 0.5, and 85% was 0.16. And then the 1/500th decay, the 75% was 1.19, 1.18 for 80%, and 1.2 for the 85%. 1/10th decay, 2.6, and for 75%, 80% was 2.64, and 85% was 2.6, which all of these were very close. Quarter decay, again, they were all very close to 3.5. And the ultimate KCU was 5.9. It varied there a little bit between 75 and 80%, but it's still very close. So then we have a different experiment that we could use to find the value of KC. And this is a model that we have an Excel spreadsheet for. And you take your parameters of K, tau, and T naught, and you plug in the KCs that help you find the damping ratio the damping that you are looking for. Here's an example of the critically damped. With our model in Excel, we found that critically damped was 0.58% per volt. So then we ran the experiment to see if that KC actually worked in the field, and it turns out it did not, and all of our numbers were way off when comparing the model to the experiment. And here, this is critically damped experiment. KC actually turned out to be 0.35, and you can tell that it's critically damped because it goes from the steady state, and as it steps up, it doesn't overshoot at all into your steady state after the step. So that tells us that it's critically damped. This is a graph of the ultimate. I kind of cut out a few of the graphs because it would take a long time to explain them all because they're all fairly the same except with different parameters. But the ultimate, you could tell that this is, the KC came out to be 1, and our system was very close. Just that 1.1, our system would oscillate the entire time. And that's how close it was. But you can tell that this is the ultimate KC because it takes a little while to settle down, but it eventually reaches steady state. And anything over 1 will constantly oscillate. And this is a plot of our design versus experimental decay ratios. You'll see how different they are. The critical decay, the KC for the design versus the experiment is 0.58 and 0.35. And then from there, the numbers get kind of crazy. Our 1/500th decay was 2.8 in the design, but it was only 0.58 in the experiment. And we went all the way up to the ultimate was 5.9 in our design, but we could not go over 1 in the experiment. And here's a graph of those results showing the difference. And here's just something I thought was kind of cool. I got taken down to the lab I was shown that there's a slightly different software down there that you can use. You can actually run your system constantly without shutting it down, and you can change your KC as it's running. And this graph here, we ran the KC at 1.2 initially for about 100 seconds, and you can see that it never stops oscillating. So just to see what happened, we bumped it up to 2, and it continued to oscillate. And then we took it up even more, and we went all the way up to 40. And you can see that the motor is going all the way down to 0 to 100, trying to get your output to a steady state, but it never could. And just a cool video. Hopefully I can get it to work here. But if you're anything like me, I'm wondering, like, oscillation, what is that really doing? What is it really showing?
Click on that again and then hit the run button. Oh, there you go.
So here's a little video to show you why the customer does not like his system to oscillate. You'll notice this was actually from that graph when it was at KC of 40, and it was going from 0 to 100% trying to reach the steady state. You see the lights are flickering, trying to find some kind of steady state. Now, if you ever reached it, of course, you'd have a constant light there, but with it oscillating, your lights are flashing the whole time. And this is just an example of why your customer would not want his controller to oscillate.